Okay. Good morning, y'all. Any questions before we start? Okay, I'm going to say a couple things about the last homework. And yes, I know that your current homework is not due till Monday, but I went ahead and posted this, and this is it. This is the last homework. So in the first one, I'm going to show kind of an interesting thing. It turns out that if you have any polynomial ring, and we'll start talking about polynomials and power series today. If you have any polynomial ring over a commutative ring of identity, it always has infinitely many maximal ideals, always. And we start off by looking at a polynomial ring fx, and I didn't say it there, but I mean that fancy f to be a field. Show that if you have a polynomial ring over a field, then this always has infinitely many maximal ideals. One case is easy. If the field f is finite, it's pretty easy. I'm sorry, if the field is infinite, it's pretty easy. If the field is finite, you have to do sort of something a little bit different. Remember, fx is actually a UFD because it's a Euclidean domain, and that might help you there a little bit. In number B, show that if R is commutative ring with identity and P is a prime ideal of R, then the ideal is Px, which just means all polynomials with all coefficients in the prime P, and P comma x, which is the smallest ideal generated by P and x, are both prime ideals of the polynomial ring Rx. And then use what you've got so far to show that if R is commutative with identity, then Rx has infinitely many maximal ideals, always. We'll see a contrast power series because actually, for example, in the polynomial ring fx, you have infinitely many maximal ideals. In the power series ring, you only have one. Number two, in this problem, we will show that an integral domain is a PID if and only if every prime ideal is principal, right? PID means every ideal is principal, but it actually suffices to show that every prime ideal is principal. For this problem, R is an integral domain. In part A, suppose that R has an ideal that is not principal. Show that R has an ideal that is maximal with respect to not being principal. If this sounds like it's Zorn's lemma, then it is. B, show that an ideal of R is maximal with respect to being non-principal. I'm sorry, show that an ideal that is maximal with respect to being non-principal is necessarily prime. This is actually an important kind of theme that happens in computer algebra a lot. Often ideals that are maximal with respect to having or sometimes not having some kind of nice property are prime. C, show that R is a PID if and only if every prime ideal is principal. So use what you've done in A and B and build on that. Of course, one direction of this is easy, the other direction is interesting. And D, show that R is a PID, and so this is a nice characterization of this. Really underscores the relationship between PID and UFD. Most of you have seen in a previous algebra course that the principal ideal domain is always UFD, right? This nails it down. R is a PID if and only if R is a small UFD. And what I mean by that is R is a UFD and of dimension no more than one. So we've seen dimension 0 domains are fields, and a one-dimensional domain is a domain in which every non-zero prime ideal is maximal, like the integers, for example. So hopefully that'll be kind of a fun one to finish off the semester. It'll be due the last day of classes. Okay. Any questions on that? Okay. So let's get back to our adventures. Turn this off here. All right. So the last thing we were talking about was this correspondence between R's commutative identity then there was a one-to-one correspondence between prime ideals of R that miss S and prime ideals of R inverse S. So and it worked this way. One freaking day, planet Earth, that's where you want to stop. This is what I get. Okay. So this is the last thing that we talked about. And you have this notational convention. This was called the localization of R as a prime ideal. And we also have this. You might ask yourself, so here's kind of a diagram why this works. So in your original ring R, you have this prime ideal. And maybe it's maximal, maybe it's not. There might even be maximal ideals contained in this, right? But I do know that its complement, everything outside of P is a saturated multiplicable closed set, right? In fact, the complement of any union of primes is a saturated multiplicable closed set. Everybody okay with that? And so if you look at RS, which is R localized to P, R localized to P, what you're doing is you're taking this set here and you're turning everything outside of it into units. These are all units out here. It's not true that everything outside of P is necessarily a unit, right? But it turns everything outside of this into units. And in fact, the only primes left by the correspondence theorem, the only primes left are primes that miss the complement of P. And what does it mean to miss the complement of P? It means it's contained inside of P. Right, so the only primes left over here are the ones that happen to live inside of P in the first place. That makes this new P localized to P a new maximum ideal. And there's only one of them. So it might be useful to see an example of this actually in action. So you've got, I can't draw them all, but you've got lots of prime ideals in the integers, right? Now, what's outside the ideal generated by 2 is certainly not all units. In fact, 3 is outside of it and 5 is outside of it, right? But what happens when you look at Z localized to 2, this is a set of A over B, where A is an integer and B is not in the ideal derivative. So that is to say B is odd. what happens here, this ideal right here, the 2 one, is the only one that survives. Everything else goes away, right? So because remember, 3 is in this ideal here. Well, now it's a unit because it's outside of, see, because 1/3 has an odd denominator. 5 is outside of the ideal generated by 2, so it's a unit as well. And in fact, every prime that is not 2 now becomes a unit, basically evaporating everything except for 2. So the only prime ideals you got left here, Z has this huge mess of ideals. You've got the 0 ideal, got the ideal generated by 2, 3, 5, and in fact, you've got infinitely many of them. Everybody agree? So if I were to draw a diagram of prime ideals, 0 is at the base, and it's like a crown, right? You got 2, 3, you've got all these one height stalks above it. What the localization does is it kills everything except for this part of the stalk. Okay. And so this allows you, one of the reasons this is important in community algebra, it allows you to localize, it allows you to get rid of all the noise that surrounds maybe some prime ideal you want to focus on. Right? And now in this new ring, you have only one maximal ideal. It's the ideal generated by the number 2 among these fractions, and everything that's not in that ideal is a unit. Because if it's not in that ideal, it's got an odd denominator, or I'm sorry, it's got an odd numerator. And an odd numerator can be inverted in this ring. Everybody okay? You could also do other things, of course, as well as C. You could take S. You could take S to be the complement of the union of these 2 prime ideals. And when you turn all the S into units here, what's left over, these are the only 2 primes left over. So when you localize at this set, you will have 2 and 3, both containing 0, and everything else is gone in the sense that it's turned into units. Okay, any questions on this? Okay, now I have to do an unfortunate job of introducing you to some real notation that I've always thought is sort of backwards. Definition. I'm only going to focus on community groups of identity, but you can extend these definitions. They're used in other contexts. We say R is quasi-local actually, I'll just make it one word, quasi-local, if R has a unique maximal ideal. It is called, and I'm not kidding, R is semi-quasi-local. Here, R has maximal ideals. It's important, and I'll show. There's more correcting from actually. Yeah, this reminds me of music. Does anybody know what a hemi demi semi quaver is? Never heard of that? It's a 64th note actually. A quaver, I think, is an eighth note. But that's a real word. They can need any city quaver. Is a 64th note. So I feel like Mozart here. We say are local. So some of you may have heard this more familiar terminology, like a local ring. If R is quasi-local. Okay. That is all ideals. So we say that R is a local ring if it has only one maximal ideal and all its ideals are finitely generated. You say R is semi-local if it is inferior and semi-quasi-local. I've always thought that was a rather mistake in the notation because I really sort of thought that local should probably just mean only one maximal ideal and then add the modifier on to describe the ideals are also finitely generated, but that's not the way it is. So quasi-local, semi-quasi-local, the quasi is the more general case. Quasi-local means only one maximal ideal, semi-quasi-local means finitely many. When you remove the quasi, that just also adds on the extra condition that all the ideals are finitely generated. So, for example, if P and R prime, then R localized P is quasi-local. If P1, P2, so if you have a finite list, R prime, and S is the complement of these finite list of primes, then R localized S is semi-quasi-local. Okay, any questions thus far? Let me give you kind of a last theorem from this section, and we'll go through this. Let R be a commutative ring with identity following or equivalent. Following conditions are equivalent. A, R is quasi-local. All non-units of R are contained in some fixed maximal ideal. M and R, and C on this bar formed an I. Okay, so these following conditions are equivalent. Okay, so let's prove this. Okay, so first thing we're going to do is we're going to assume that R is quasi-local. So that means, remember what that means? It means it's only got one maximum ideal. And B, all non-units of R are contained in some fixed maximum ideal M and R. Well, R is quasi-local with unique maximum ideal M. Okay, so if you've got that by assumption, be a non-unit, an arbitrary non-unit, then I claim that any X is contained in this particular maximum ideal M. Right? Notice the ideal generated by X is proper. So X is contained in N for some maximum ideal we know that that's a big theorem from computed algebra, that if you have any proper ideals contained in some maximum ideal, but here you have no choice. There's only one maximum ideal. So X is contained in M, therefore X is in M. And we proved the statement here that all non-units are contained in this particular fixed maximum ideal. So all non-units are contained in M. So if N equals a set of non-units, so I don't claim that's an ideal yet, I just claim it's a set. Then N is a subset of M, therefore the ideal generated by N is contained in the maximum ideal M. So right. So it remains to show N equals N, right? Because what I know so far is I know the set of non-units generates a maximum ideal. Or I'm sorry, the set of units, the set of non-units generates an ideal, which is necessarily contained in this maximum ideal. But I guess the statement here is all non-units form an ideal. So clearly, the non-units are contained in the ideal generated by the non-units. Now, for the other containment, suppose the non-units is not contained in N, then there exists U, a unit in this words, you have to be able to generate a unit with these non-units. Therefore, U is in the ideal generated by N, which is in M, which is a contradiction. Because no maximal ideal, in fact, no proper ideal at all, contain a unit. Everybody understand that?
So you said that no maximal ideal contains a unit.
No proper ideal at all.
No proper ideal at all.
And then what we do know is this thing is trapped inside of this maximal ideal.
Can you just say like a little bit more about the no proper ideal?
Well, because if you have, let U be a unit, then U inverse is in I, therefore 1 is in I, and therefore,
Oh, that's fine.
yeah, all over the place, having an identity is
Right.
super, super powerful.
Okay, so if you have a unit, you automatically have an identity.
That is correct. The final thing we need to do is show the seam blase. Right? So we assume that all non-units form an ideal. We need to show there's only one of them. So what I want to do, so here's my strategy. I'm going to show that I have two maximal ideals that are the same. So let M and N be maximal ideals. Okay. Suppose there exists M suppose there exists M, it's in M, but not in M. Let's suppose there exists such a thing. Since M is not in N, and maximal, the ideal generated by N and this new element M must be all of R. Agreed? Because this ideal strictly contains N, because N doesn't contain this, because of the maximality that sets the floor of the whole ring. So there exists N and N and R and R. N plus Rm equals 1. And this is a problem because note M and N are non-units. And I didn't say this in the statement here, and I should have, because otherwise the statement is, this is always true if you're going to allow it to be the whole way this forms a proper ideal. M and N are non-units. So the ideal generated by N is contained in the ideal generated by all non-units, which is strictly contained in R. Therefore, 1 not in N. So what can we conclude? What we can conclude is, so there is no M in M that is not an N. Right? right? Because if there's an M and N that's not an N, we run into this contradiction. Therefore, M is contained in N. But M is maximal. So, and we conclude that R is quasi-local because there's only one maximal. Any two maximizers have equal each other. Okay. Any questions? Okay. So now I'm going to go through. So here's the strategy. We're going to talk about polynomial power series rings. And I think that, so I might go fast in some places. So don't be shy to slow me down if you like, because backgrounds can be different. But I am assuming that you all have worked with polynomials and power series enough to know what the degree is, for example. And for example, if I have a degree 5 polynomial times a degree 3 polynomial, and you multiply them together, what do you expect to get? I would expect to get a degree 8. You have to be a little careful there. That's true if it's an integral domain. Alexis, slow me down. I'm going to start actually from the point of view of power series. How many of you have looked at power series before? You certainly looked at them in calc too, right? But again, you make a mistake trying to plug in a bunch of crap for that. We just treat power series like symbols in the following sense. So let's get rolling on this theorem. So I'm going to introduce this sort of as my theorem thing. I'm going to actually build power series first, which is probably, some people might argue for that, because from a topological point of view, and you can also argue from an algebraic point of view, you build polynomial first in power series. So I'm sort of like going from the real back to the rational. But this is basically the same tack. It's very similar to what we did earlier. This is like starting with the direct product and defining the direct sum to be a subgroup. So the set of formal power series, and we call this formal because we treat this just like a symbol and multiply by a symbol. We don't worry about things like convergence, at least not at this point. This is the set of formal power series with addition defined this way. Number one. By the way, you might notice that what this really is actively is this is isomorphic to the direct product of a bunch of abelian groups. Basically, the x's act as a basis, they're just placeholders, right? And it's a direct product because all the AIs could be one, right? Or something like that. There are no restrictions yet. And so what you have is you have this sort of countable direct product, and you just add coordinate-wise. That's all that's going on here. The multiplication is kind of a graded thing. It's a little bit more tricky, but not too bad, because really, I think you all are all kind of sort of familiar in your guts with how to multiply polynomials. And it's the same, it just goes on forever. 2. How are you going to multiply these things? Because I do want to turn this into a ring. Well, way that I'm gonna make a new power series this way. And I've got to see what the ceilings are. So, I guess it's going to be AK. So in other words, what this means, so this is not part of my definition. So if you like to take notes, that's fine. I'm not finished my definition. I'm taking a little aside here to do something. So for example, if A0, say 1x plus A2x squared. And B0 plus B1x, B2x squared. What you do is you just multiply and group sort of the like degrees together, right? So, and you got to start at the bottom, right? Because there's no guarantee the power series will ever end, unlike polynomials. I'm used to like multiplying the biggest terms on the polynomial first. You can't necessarily do that here. That's the constant term. And then the x term is given to me by A1B0 plus A0B1. And notice that the subscripts always add up to 1, right? X squared A2B0 plus A1B1 plus A0B2. And you just keep going like this, right? That's what the formula says. For the nth degree term, it gets bigger and bigger. But notice that this product makes sense because at any finite place, I can compute all the coefficients, right? This, with this definition, is the formal power series. So let me write it this way. Our power x is a ring. And in fact, if R is commutative, then so is this. If R is non-commutative, you can do it as well. It's generally assumed for one variable that the elements in R commute with X, so you don't have to worry about that. And if R has an identity, this does. The identity power series, if you look at the way that we multiply things, it's just the power series 1, right? And Rx, we define this way, is equal to the set of power series such that actually, let me write it there this way. Clear. This way. Such that A(n) equals 0 almost everywhere. So in other words, all the finitely many coefficients in the power series have to be 0. And what does that give you? That gives you a polynomial because you have to end at an infinite string of zeros. Let me make a couple of notes here before I get into kind of sort of the technical things like degree and so forth. Note. What does it mean to be a polynomial ring in 2 variables? Well, you can sort of deductively do this. I know what that is, and then add enough variables, right? And more generally, So inductively, you can define it this way. I even know and similarly, you can do the same thing for forming power series as well, right? So you can have multiple variables in the power series. I can even do infinitely many variables. And I know what this means because this is sort of over right. So what it means to be a polynomial, even in uncountably many variables, is, for example, if I had a polynomial ring in variables that were indexed by the real numbers, so I have x sub 1, x sub 2, x sub square root of 2, x of any real number I wanted, that is certainly an uncountable ring because you've got uncountably many variables, but there's no real confusion as to how to write a polynomial, because if I give you any polynomial, even though I can potentially use uncountably many variables, I can only use finitely many at a time, right? So a typical element of even a large index set like this will only involve finitely many variables. So a typical element lives in one of these things right here. Everybody okay? Now, I am not going to, in this class, you'll have to come up to me later to do this. In this class, I will not discuss power series and infinitely many variables, because that is more murky. In fact, there are 3 distinct definitions of what power series and infinitely many variables mean, depending on how you want to do it. You can do it as a union of nets, and you can do it as sort of different symbols where you're allowed to. In fact, you might think about that. I'll leave it as an exercise to sort of think about what is the problem with even countably many power series variables. What's the ambiguity there? Or what are a couple of ways you can do this to get competing definitions? Okay. So let's do this here. Definition. But after that, and I'll say that these terms not 0. I'll say that the leading term, the largest, the coefficient of x to the n is not 0, because otherwise I would have written it in a smaller way. We define the degree of f to the n. So the degree of f is just the power you see on the largest non-zero coefficient. This is completely well defined, except for the ambiguities. What do you do with the 0 polynomial? With the 0 polynomial, there is no non-zero coefficient. It depends. Some people say it's undefined. For the purposes of this class, we will say that the degree zero polynomial. Well, I might say it does not exist sometimes, or I might say it's minus infinity. Okay, I think I need that for the next things. I should check that. And for a power series, of the form g of x equals times the sum a equals 0 to infinity, and here I'm going to say R0 is not 0. So really what I've done here is x, right, so R0 is the first, R0 is the sort of first non-zero coefficient of the polynomial, or the power series. Notice that the smallest degree term that you see here is x to the n times R0. All right. In this case, we say the order of f of x, or g of x. So is equal to n. And we will say that the order of 0 is infinity, or it's not. But I think that those two, will jive well with this next proposition. Let me get this written down and see if it makes sense. Let's check our order and degree of 0 case. Let f and g be polynomials and alpha and beta be power series. Polynomials and alpha, beta are power series. Then a degree of x g of x is less than or equal to the degree of f of x plus degree of g. And equality holds if the leading coefficient of f or g is not a 0 5. So if I define the degree of 0 to be negative infinity, negative infinity plus 10 or equal to. So that makes sense.
When you say the leading coefficient of f, you mean like neither of them can be a zero driver?
No, you just need one of them, not be a 0 5. Degree of f times g is less than or equal to max of 3f 3g. And we get a similar sort of thing for the ORD. The ORD of alpha beta is, yeah, I get actually, it's very are equal to 4 alpha plus 4 beta, equality holds. You know, smallest terms of either a alpha or beta non-zero. And B, I'm sorry, what's that? So if you look before, it's usually equal to, but what can happen is you get 0, and this is actually bigger than or equal to the order of the sum. Right? Yeah, that's right. Flip from the other. And this one too, because what we have is order of alpha plus beta. Greater than or equal to the order of alpha. Or, I'm sorry. There we go. That's so think about why this is true. You usually get equalities for these things. For example, if you have an integral on that. Okay. Any questions on that? Any questions out there? All right. Well, you all. Oh, let me recommend the math club today too. We've got this guy named Matt Devine who's visiting. He was a master, so he was one of you all many years ago. He got his master's, I believe it was in '88, and he went on and was something of a muckety muck at IBM, and he's actually kind of done a pretty full career, and now he's started this kind of local thing where he's helping out socioeconomically disadvantaged people, helping them with math and things like that. So that ought to be pretty interesting, and it shows just another thing that you can do with all this. So I recommend y'all being there. Other than that, have a good weekend. We will see you on Monday.